Okay, good morning. Welcome to VSPG. Today we're hearing from Dr. Chad Ostrander from the University of Utah talking about the thallium isotopic system, the platypus of metals. And I will go ahead and introduce Chad for us. So Dr. Chad Ostrander is an isotope geochemist who applies isotope systems, including vanadium, iron, molybdenum, uranium, and thallium, to a variety of paleoceanographic questions. His work is often focused on paleocean redox and Earth's oxygenation, and how these factors have influenced the evolution of early life. He also applies these systems in modern settings like the Baltic Sea to ground truth their uses and apply his expertise towards a better understanding of trace metal isotope cycling in the present. Chad received his bachelor's and PhD from Arizona State University, where he worked with Dr. Ariel Anbar, applying molybdenum thallium isotopes to paleo-redox-related questions on a variety of Precambrian rock and Archean and Proterozoic. After his PhD, Chad did his postdoctoral fellowship at Woods Hole Oceanographic Institution, continuing his work with trace metal isotopes. And Chad, we're really excited to hear about thallium today. So go ahead and take it away.
Awesome. Well, thank you for the introduction, Alex, and thanks to you, Andre, and all the others behind the scenes for giving me the invite today. It's a pleasure to speak with the community here. It's a wonderful opportunity to get a lot of Precambrian geochemists in one room, and I really like how these get posted on YouTube. So you can increase the viewership. It's a really unique opportunity. Thanks. And so, yeah, as Alex had said, my name is Chad Ostrander. I'm an isotope geochemist. Today, the title of my talk is Thallium, the Platypus of Metals. This isn't a title that I'm giving to thallium. It's an old dead scientist gave thallium this title. And you'll hear more about that in a couple of slides. But yeah, I just started on the faculty at the University of Utah. And so I'm in the Department of Geology and Geophysics there. Been there since July. So I just got there. But yeah, a mixture of, I'm a trained non-traditional isotope geochemist, but a mixture of applications to the ancient rock record, as well as ground truthing in modern systems to really understand what the heck these isotopes mean and how we can better interpret the trends in the ancient rock record. Right, so my research focus, like many of you in this room, is Precambrian, but even more specifically, Precambrian oxygenation. And so we've made a lot of progress over the past century or so in understanding the history of oxygen on Earth. So those of you who are on the call today have your own opinions of how this figure should look, but this is kind of a generalized idea of how atmospheric and marine oxygen has evolved through Earth's history for the past 4 billion years. So most would not argue with the idea of a great oxidation event shortly after the Archean Proterozoic boundary, after which oxygen first accumulated in the atmosphere's non-trace levels. It's also at that time that we start to get some oxygen accumulation in shallow marine environments. There's evidence for perhaps oxygen before the GOE. I'll talk a little bit more about that later in my presentation. And it's not really until the Proterozoic-Phanerozoic boundary that you get another huge stepwise change in atmospheric and ocean oxygenation. And so it's currently being debated when that is and how intense it was. But most would agree with the idea that you have perhaps near modern levels of oxygen sometime early in the Phanerozoic at least. And so today I'm going to focus on Precambrian marine oxygenation, but more specifically, the timeframes in Earth's history that I've spent the most time researching and thinking about. And so I've worked at this point essentially all across the geological timeframes from modern day all the way to about 2.7 billion years ago. But two timeframes that have most of my attention to this point are the two major transitions in Earth's history. And so specifically the Great Oxidation Event, so the initial rise of oxygen in Earth's atmosphere and also in the ocean. And then this idea of a Neoproterozoic oxygenation event close to the Phanerozoic-Proterozoic boundary. So the Great Oxidation Event is important because this is the first time that oxygen becomes a non-trace level gas in the atmosphere, and you start to get a lot of oxygen accumulating in at least shallow marine environments. And the Neoproterozoic oxygenation event is really important because coeval to evidence of this potential oxygenation event, you have fossilized animals first appear on the rock record in the Ediacaran period. So this history of oxygen in our oceans specifically has played a key role in the habitability of Earth's surface. My talk is going to be split into two parts. I'll talk with an introduction to the thallium isotope paleoredox proxy in part one, and then in part two, I'll talk about applications to the Precambrian record. I thought it was important to spend quite a bit of time on part one because thallium isotopes is, at least compared to some of these other paleoredox systems, a relatively new proxy. And so it's worth kind of fleshing out why thallium is useful to those who, there's only a few of us who think about thallium a lot. And so maybe be nice to give a long introduction. This will live on YouTube for as long as the internet's alive, hopefully. And so if anyone wants to learn more about how thallium isotopes work, you can go to YouTube and check us out later. So today's protagonist is thallium, the platypus of metals. And so it was realized very early on that thallium was quite an odd element. So thallium behaves in some settings as a lithophile element, so it's rock loving, but in other settings it can behave like a chalcophile element, and so it's sulfur loving. When thallium was first discovered, the emission spectra that it gave off looked like an alkali metal. It was a sharp green line. That's where thallium gets its name. It means green twig. And so one of these French scientists who helped discover thallium had this quote in the late 1800s: "Thallium is destined to make an epoch in the history of chemistry through the astonishing contrast that appears between its chemical characteristics and its physical properties. It is no exaggeration to say that from the point of view of the generally accepted classification of metals, thallium offers a combination of contradictory properties which would authorize us to call it the paradoxical metal, the ornithorhynchus of metals." And so ornithorhynchus is a duck-billed platypus. And so I'm going to run with that playful title, thallium as the platypus of metals, for that reason. Thallium has two stable isotopes. That's why we're able to do all these games I'm going to talk about with it. All thallium atoms have 81 protons. That's what identifies them as thallium, but you can have a stable nucleus with different numbers of neutrons. There's two stable nucleus configurations, one with a total mass of 203 and another with a total mass of 205. Thallium 205 is the most abundant of the isotopes at our surface today. All of the thallium isotope data that I'm going to talk about today, and as a community, we do the same thing. We report it all in epsilon notation, so epsilon 205 thallium. And for all intensive purposes, this is the same as delta notation. What it turns out, the reasoning for this epsilon notation is that thallium being a really heavy element, the relative mass difference of the two isotopes is pretty small. And so it was thought early on, you wouldn't get a lot of thallium isotope fractionation. And so because the thallium isotope ratio differences were going to be so small, we were going to need to multiply these ratios by 10,000 to get nice round single numbers to play around with. And so it actually turns out that thallium isotope fractionation today is actually quite large. It rivals that of iron, a much lighter element. And it has to do with the fact that thallium is subjected to these really unique nuclear field shift effects that can drive these large fractionations. But throughout this talk, when I talk about thallium isotope compositions that are higher, heavier, more positive, I'm just talking about things that are more enriched in thallium 205 and vice versa. When I'm talking about things that are lighter, lower, or have more negative values, those are things that are enriched in the lighter mass thallium isotope, thallium 203. This is a fun plot to show kind of how thallium stacks up against the other paleoredox proxies in terms of applications. And so since the invention of the multi-collector ICP-MS around the turn of the century, these are all paleoredox proxy-specific applications that are published. Molybdenum isotopes kind of took off really quickly, largely because of some findings from the Black Sea. It turned out that molybdenum isotopes in the Black Sea behaved in a way that seemed to make them useful for reconstructing Earth's past environments, and so scientists have been running with that since. It wasn't until much later that uranium isotopes kind of came to the forefront. First off, it wasn't thought that uranium isotopes were going to fractionate very strongly because it's such a heavy element, but turns out that uranium isotopes do fractionate in a magnitude that we can measure with multi-collector ICP-MS. And it actually turns out that uranium isotopes are a really useful paleoredox proxy in carbonates. And so this is the uniqueness of uranium, is you can apply it to the carbonate record. And so since shortly after 2007 or so, uranium isotopes have kind of taken off. And so there's a lot of applications with uranium isotopes. Meanwhile, thallium isotopes, there's not nearly as much applications at all. It's worth noting that the earliest thallium isotope papers were being published at the same time the earliest molybdenum and uranium isotope papers were being published. These measurements have been made for the same amount of time, but this paleoredox proxy application is fairly new. My guess is that it has to do with the fact that thallium is just kind of an odd element. We've used molybdenum and uranium even before the invention of the multi-collector to tell us things about paleoredox. The concentrations of these elements and shales has been informative. You have detrital uraninite grains in the Archean and early Proterozoic record that are informative. Thallium has never had that purpose until we've been able to measure its isotopes. So that's my hypothesis of why it's lagging. It's not the chemistry that's holding it back. It's actually pretty easy chemistry and measurement to perform. And so in my mind, in order to be an effective paleoredox proxy, and so for those who aren't aware of the definition of that, it's just, something we can use to reconstruct past redox. It's our proxy for that ancient redox. In order to be able to be an effective paleoredox proxy, a tool has to be able to do two things, or have two things. It needs to have a unique redox sensitivity, and it has to have a reliable archive for reconstructing this sensitivity. If a tool is not uniquely sensitive to anything, you'll get ambiguous results. And if it doesn't have a reliable archive, you have no chance or hope of reconstructing this redox sensitivity in Earth's past. So it has to, in my mind, be able to do these two things very well. So for thallium isotopes, what are thallium isotopes uniquely sensitive to? Well, it turns out that thallium isotopes are really sensitive to manganese oxide minerals. And so if you look at thallium concentrations and isotopes in different reservoirs at Earth's surface today, by far, the highest thallium concentrations you will find are in iron manganese crusts and nodules, so ferromanganese crusts and nodules. And the heaviest thallium isotope compositions, or the highest thallium isotope compositions, are also found in those same crusts and nodules. And so nothing concentrates thallium as strongly or fractionates it as positively as ferromanganese crusts and nodules. It's not even close. So this is on the order of close to 2 per mil, or 20 epsilon units. What's happening here a little bit more intimately is that thallium in aqueous solution is stable primarily as thallium plus. When thallium is absorbed to the surface of a manganese oxide mineral, in some of these manganese oxide minerals, the thallium plus will be oxidized to thallium 3 plus, and it's this oxidation that drives a positive isotope fractionation effect. And it's this positive isotope fractionation that's redox driven, but it's also owed partly to nuclear field shift effects. And so one thing that really shows how uniquely sensitive thallium is to manganese oxides is that this isotope fractionation is mineral specific. You only see oxidation of thallium plus to thallium 3 plus today so far on the surface of hexagonal bernesite. So hexagonal bernesite is this manganese oxide mineral that has really large vacancy sites. Thallium plus is a really large ion. It's about the same size as potassium plus. And so it's this mineral that has vacancy sites large enough to actually do this oxidation. And so it's only in this hexagonal bernesite you get these 2 per mil or 20 epsilon unit shifts. Other manganese oxide minerals like triclinic bernesite or todorokite, or iron oxide like ferrihydrite, will fractionate thallium isotopes, but not nearly as strongly. So this sensitivity is unique to manganese oxides, and even more than that, specific to manganese oxide minerals. And this is really neat and nice for the proxy because hexagonal bernesite is the type of manganese oxide mineral that gets really concentrated in hydrogenetic manganese oxide deposits. And so manganese oxides that precipitate directly from cold, well-oxygenated deep seawater today, these hydrogenetic manganese oxides are composed primarily of hexagonal bernesite. These are the circles on Mark Ray Camper's plot here, and they are the most strongly fractionated. Whereas if you have manganese oxides forming diagenetically or in hydrothermal systems, it's primarily todorokite or triclinic bernesite in those settings, and you don't get as strong of a fractionation. And so those experimental results actually were that I showed in the previous slide. There was evidence for kind of the same early on in some of these early studies by Mark Ray Camper in 2002. And so these are diagenetic and hydrothermal and hydrogenetic manganese crusts. They're a mixture of all three types. And so even some of the positive fractionation we see in the other types are probably due to this hydrogenetic manganese oxide, hexagonal bernesite. So it's really unique. And so this link between thallium isotopes and manganese oxides is what makes thallium a viable proxy to track ancient oxygen. To be clear here and to state it up front, it's not that thallium isotopes are sensitive directly to oxygen. very few proxies are. Thallium isotopes are sensitive to manganese oxides, and it's the manganese oxides that are sensitive to oxygen. So if you go to marine settings today, where you have molecular oxygen present persistently in marine bottom waters, you can form manganese oxides near the sediment water interface and bury them over long time scales. That's what happens in these ferromanganese crust and nodule deposits. In contrast, if you have no oxygen in bottom waters, or if the oxygen penetration in the marine sediments isn't very strong, you can perhaps form manganese oxides, but they don't get buried over long time scales in sediments. And so because you don't have long-term burial of these manganese oxides, any net isotope fractionation effects are mole. They get zeroed out. This all has to do with the fact that manganese oxides are really unstable in the absence of O2. And so if you take oxygen away, it gets really hard to produce things like nitrate. And so manganese oxides becomes the most efficient electron acceptor, and so is thus readily reduced if you don't have things that are much more oxidized around. And so if you look at the ocean today, we have a lot of oxygen in the ocean. We have oxygen everywhere. For the most part, with little exception, we have oxygen present in all shallow environments, oxygen present in the mid-depths, as well as oxygen in the deep ocean. And in all these settings, you're forming and burying manganese oxides in sediments. And this is a process, again, that concentrates the heavier mass thallium isotope, and this leaves seawater enriched in the complement, isotopically light thallium. So just to kind of show that with numbers, thallium that's coming into the ocean today has an isotopic composition of -2 epsilon units, but seawater is much lighter at -6, and so it implies there's a sink for heavy thallium. Another way to visualize this, again, seawater, everything's coming in at -2 epsilon units. Seawater is isotopically light. That means that there's a sink with a preference for the heavier mass isotope. The only sink that can do that is these manganese oxide-rich marine sediments, ferromanganese nodules and crusts. They're the two prominent sinks for thallium. Low temperature basalt alteration has just a minor negative isotope fractionation effect, and reducing sediments, and so sediments that are quite rare today, but present nonetheless, reducing sediments don't fractionate thallium isotopes at all. And so there's a little bit of foreshadowing there. Because reducing sediments do not fractionate thallium isotopes, they serve as a good archive for seawater thallium isotope compositions. So you go to locations of the ocean today, like anoxic or euxinic basins, and the thallium isotope composition of the water column is transferred to sediments in those locations. And you can even go to places like modern upwelling zones or oxygen minimum zones, and the sediments below those settings also capture the seawater thallium isotope composition. And for those of you who are familiar with the uranium or molybdenum isotope proxies, that's really unique, because if you were to look at oxygen minimum zone sediments, which has been done for uranium or molybdenum isotopes, that's not the case. They do not capture similar values. You get fractionations that complicate the archive and that sink in your mass balance models. But thallium only really seems to care about manganese oxides. And so what's happening a little bit more intimately here is that it seems that thallium is being removed in association with sulfides, either with no isotope fractionation, or thallium is being removed near quantitatively, and it's not allowing for the expression of any isotope fractionation effects. So all the thallium isotope composition, that's compositions from modern sediments today, and all the stuff we're pulling out from the ancient rock record, is all authigenic thallium that's leached from sedimentary sulfides. And so through the rest of this talk, a lot of the thallium isotope compositions you'll see have a subscript, and that's just authigenic thallium isotope compositions leached from sedimentary sulfides like pyrite. And it's worth noting that this authigenic thallium fraction is most oftentimes the dominant thallium pool in the sediments. And so it's not like we're extracting a very small percentage of the total thallium. Most oftentimes it's between like 40 and 80% of the thallium we get off is from the sulfides. It's a major fraction, especially in sediments and sedimentary rocks formed under anoxic conditions. And it has to do with the fact that sulfides are just so darn efficient at removing thallium. You can really accumulate it very strongly. So to kind of show a little bit more detail about the oxygen minimum zone data set, this is work from Yi Wang at Woods Hole, who's doing her postdoc with myself and Andy. At the same time, she's now at Tulane, but she went to various upwelling zones today and looked at thallium isotope compositions in sediments underlying these oxygen minimum zones. And a lot of these settings capture the seawater thallium isotope composition, -6 epsilon units. And you really see what I think is a pretty coherent trend between manganese contents and thallium isotopes. So this just really shows you that thallium really only cares about manganese oxides. These upwelling zones have oxygen in the bottom waters, but they're really productive, and so you get a lot of organic matter into sediments. And so you get really reducing conditions in sediment pore waters pretty shallowly. But in some of these settings, you can bury manganese oxides, and so those sediments will have really high manganese contents. And when you have high manganese contents, by extension, high amounts of manganese oxides, you shift the local sedimentary thallium isotope composition heavy. And so even in these anoxic or reducing rather sediments, it's all tied to manganese oxides. Thallium really only seems to care about manganese oxides. And when the manganese oxides aren't around, you can capture the seawater value. And so just to kind of get a little bit more redundant here is sediments formed in anoxic basins have no isotope fractionation. And so this is the difference between the thallium isotope composition of the water column and the sediment. If you go to these reducing settings, in settings where oxygen penetration depths or our bottom water oxygen contents are really low, you get close to capturing the seawater value. If you increase the amount of oxygen in marine bottom waters, you get shifted towards heavy values. And all has to do with how much manganese oxides you're able to accumulate in those settings. And then when you go into these manganese oxide rich sediments, it's where you get the really large effects where you're predominantly manganese oxides. So ferromanganese crusted nodules that are hydrogenetic have the strongest effect, whereas diagenetic and hydrothermal sediments are muted. And so again, these hydrogenetic ferromanganese crusted nodules are these types of sediments that are forming really deep on the seafloor. You're talking kilometers. And so because this is or actually one more slide, even in these upwelling zones, you see kind of a depth control where sediments recovered from oxygen minimum zones, as you get further away from shore, you get stronger effects. And so the thallium isotope fractionation seems to be strongest in these deep deposits that are forming and bearing manganese oxides really efficiently. And so this is kind of all hopefully coming to a point here to say that there's reason to suspect that with all this data we're pulling from modern settings and data we're getting from experience, thallium isotopes could be a proxy uniquely sensitive to deep marine oxygenation. The strongest thallium isotope fractionation effects are pulled from these ferromanganese crusted nodules that form and accumulate very slowly on the deep sea floor. And so it could be, and we've done this in some of our studies, leveraged as a proxy for specifically deep marine oxygenation. So it's not just oxygenation in general of the ocean, but deep marine oxygenation. And so you might think of something kind of opposite of like iodine calcium. Iodine calcium and carbonates is a good proxy for surface water, ocean oxygenation. Thallium is potentially a good complement for the deep marine environments. But at the very least, it seems to be a proxy that's really good at tracking bottom water oxygenation. And so again, if you have bottom waters that are oxygenated and you have really strong oxygen penetration depths in the sediment pore waters, you can bury manganese oxides. If sediment pore water oxygen penetration is not strong, you don't bury the manganese oxides. And so in order to drive these large net positive isotope fractionation effects, it's really hard to do this without burying manganese oxides in sediments in the presence of oxygen in the bottom waters. And so I've told you all of the good, and it's therefore also, equitable to tell you about the bad. If there is a Achilles heel for thallium isotopes, it's basin restriction. And so what we find in all the settings we've been studying today, here's an example of some data we're pulling from the Baltic Sea. This is work it's been submitted. It was in prep the last time I presented this, is that the seawater thallium isotope composition of the open ocean today is -6 epsilon units, but you go to places like the Baltic Sea, one of these good ancient earth analogs we like to study, and the thallium isotope composition of the Baltic Sea does not match open ocean seawater. The thallium isotope composition of the Baltic Sea matches thallium inputs into the Baltic Sea. And we see this also in the Black Sea. The Black Sea has a thallium isotope composition equal to nearby rivers. And so most of the thallium that's getting delivered to these semi-enclosed basins is coming from rivers. And so this is the Achilles heel for thallium, is if we look in the ancient rock record, we have to try to do our best to screen samples that come from open ocean marine settings. But one thing that's worth noting here is that even though the thallium isotope composition of the water bodies of these semi-enclosed basins does not match to open ocean seawater, the sediments forming below the oxycline in these settings still capture this seawater thallium isotope composition. So the archive seems robust. It's just whether that's an open ocean signal is something that takes careful consideration. So rounding out circling back to kind of what I thought were two important qualities of an effective paleoredox proxy, thallium seems to check those boxes. Thallium has a unique redox sensitivity. It's uniquely sensitive to manganese oxides. And through this information, we're pulling out even more intimately, perhaps sensitive to bottom water oxygenation, if not deep marine oxygenation. And the archive for seawater thallium isotopes seems to be really strong. It's really easy to capture a seawater thallium isotope composition. You can compare this to molybdenum isotopes, where it's extremely difficult. So this is a Precambrian geology seminar. I haven't shown any Precambrian data. So for the last part of my talk, I'm going to do that. I'm going to talk about the applications of thallium isotopes to the Precambrian sedimentary record. And as promised at the beginning, I'm going to focus on two timeframes. So the two timeframes that I've spent the most time studying. This is the Great Oxidation Event around the Archean Proterozoic transition, as well as this idea of a Neoproterozoic oxygenation event in the Neoproterozoic during the rise of animals. So we'll move forward in time from the GOE. So it's not a surprise to anyone in this Zoom room that the idea of oxygen at our surface before the Great Oxidation Event is a topic that is debated. So some scientists would argue that the Great Oxidation Event was a kind of like a light switch where we had no oxygen, maybe cyanobacteria evolved, and then bada bing, bada boom, there's the GOE, it's done and over with. Others would argue that oxygen was being produced long before the Great Oxidation Event, but it took time for O2 inputs to be stronger than O2 outputs. And so it's just a mass balance game. You need Earth's surface to evolve biogeochemically in order to be conducive to oxygenation, to tip the scales in favor of oxygen production. And so myself, coming from the lab at ASU, of course, I have stock in the whiffs of oxygen debate. And so there's this idea that's grounded in empirical data from the 2.5 billion-year-old Mount Macrae shale from Western Australia, that there's a lot of geochemical signatures in this rock, which is deposited firmly before the Great Oxidation Event. This is a rock that still bears sulfur MIF signals. This is a rock that's being formed under an atmosphere with trace levels of gas, trace levels of O2 in the atmosphere. So it's a firmly pre-GOE shale, but nonetheless, there's geochemical evidence in this shale that suggests that there was probably oxygen around at Earth's surface, at least transiently, 2.5 billion years ago. And so there's this idea of a whiff of oxygen before the Great Oxidation Event. However, this is an idea that is not free from controversy. There is a recent back and forth in Science Advances from two separate groups. Being truthful, you're going to get my view because I'm part of the team rebutting against the attacks on it. But yeah, nonetheless, there's ideas that the whiff of oxygen, the geochemical data can be explained in another way. And so this is just to say that it's a topic that's debated, and there's evidence in support of both camps. But I would argue, and we do in this technical comment, is a rebuttal that the evidence still seems to be in favor of the oxygenation event. But if you're interested and you don't know the story, feel free to look at the back and forth. So thallium isotopes, we thought when we started this study that this is a unique opportunity to apply thallium isotopes to a set of rocks to try to learn new information or test this idea of a whiff of oxygen. The whiff of oxygen hypothesis is primarily an atmospheric story, and so there's reason to suspect, based on the geochemistry of the Mount Macrae shale and coeval rocks from South Africa, that there was a small amount of oxidative weathering on the continents. But what we wanted to do with thallium isotopes was, can we find evidence of oxygen, but more specifically in the ocean during the whiff? And so we can come to the Mount Macrae shale with a prediction. The Mount Macrae shale was deposited under locally anoxic conditions, and so it should be a good archival. It should be a good archive for seawater thallium isotope compositions. And if that's the case, then if there was sufficient oxygen in the ocean during the whiff to form and bury manganese oxides and sediments over a region of the seafloor, that should be able to drive seawater to a lighter value, and we should capture that lighter value in this setting that the Mount Macrae shale was deposited in. So again, during the whiff, we should expect to see this shift towards lighter values. And so we fleshed this out in a couple of papers. This is a modified figure from a paper we published in 2022 in Frontiers in Earth Science. The Mount Macrae shale is the shale that hosts the whiff interval that's in purple here, and specifically the upper shale member. But we wanted to build a longer term history of thallium isotopes in seawater leading up to the WIF and during the WIF. And so this is a compilation from 2 different studies, but published in 2022. And so leading up to the WIF, we actually find thallium isotope compositions in the Whitnum and Mount Sylvia formations that are near crustal. And so they're not fractionated relative to upper continental crust. They're not fractionated relative to riverine input today. And so there's little reason to suspect that there was manganese oxides being buried over large areas of the seafloor during the formation of these rocks. However, when you move into the Mount McRae Shale, and especially the upper shale member, you get a shift towards lighter thallium isotope compositions. And so that hypothesis seems to be supported by these data, a negative shift during the WIF interval that could suggest manganese oxide burial on the seafloor. In the first study of these rocks in the Mount McRae Shale, though, we didn't just apply thallium isotopes to these rocks, we applied molybdenum isotopes as well. And so there was already some existing molybdenum isotope data, but we increased the data resolution in this study in 2019. And molybdenum isotopes, for various reasons, are a complicated proxy and can lead to ambiguous results because it just seems to be not have a unique redox sensitivity. There's a lot of things that can fractionate molybdenum isotopes. One of the things that fractionates molybdenum isotopes, though, is manganese oxide minerals, just like thallium. However, when the molybdenum isotope sensitivity to manganese oxides is in the opposite direction as thallium isotopes. And so manganese oxide minerals on the seafloor today have really light molybdenum isotope compositions. And because these sediments are being formed and buried over wide areas of the seafloor today, this drives seawater to be really heavy today. Seawater molybdenum isotope composition is really heavy. It's plus 2.3 per mil. And so knowing how molybdenum and thallium behave when absorbed to manganese oxides, we can come at the Mount McRae Shale with a prediction that if we apply both of these systems to the Mount McRae Shale, and they're both tracking manganese oxide burial, then we should expect to see this anti-correlation whereby you're forming a lot of manganese oxides on the seafloor. This will take up isotopically heavy thallium and light molybdenum, and it would drive the opposite signals in seawater. And so when we applied this to the Mount McRae Shale and to the rocks immediately underlying it, we see that there is not much of an anti-correlation leading up to the event, but when you go into the WIF interval, there's a really strong anti-correlation between molybdenum isotopes and thallium isotopes in the Mount McRae Shale. And so it seems to really support that manganese oxide burial hypothesis. And so this was results that were published originally in the 2019 Nature Geoscience paper for myself and others. But we see what we think is a really strong anti-correlation between thallium and molybdenum isotopes in the upper Mount McRae Shale. You can see that in the cross plot as well. And so there's intervals during Mount McRae Shale deposition when there seems to have been a lot of manganese oxides being buried. And so in the lowermost upper shale member, you have a shift towards heavy molybdenum and light thallium, and it's not as statistically coherent, much higher in the section, but nonetheless, it does seem to come back to that anti-correlation near the top. But these 2 intervals highlighted in green seem to be episodes of widespread manganese oxide burial. And so in this paper, knowing what thallium isotopes are uniquely sensitive to, we made a case that you had to have molecular oxygen present in marine bottom waters over a region of the seafloor to bury manganese oxides over a region of the seafloor and drive this seawater anti-correlation with thallium and molybdenum isotopes. And so it was an idea of, in order to get oxygen in marine bottom waters, it has to basically be present throughout the entire water column. You have oxygen production in the surface waters, and this oxygen is even accumulating in bottom waters. And so there's this idea in the title of our paper is fully oxygenated water columns over continental shelves before the GOE. And this really suggests a lot more oxygen before the GOE and during the WIF than was previously thought. There was ideas that there's some geochemical signatures that suggest some oxygen accumulation, but our paper, again, knowing the sensitivity of thallium, seems to suggest oxygen accumulation in marine bottom waters. So it's another line of evidence that supports this WIF hypothesis. It's really hard to explain these trends in any other way. So zooming out a little bit, what do these data kind of support for the GOE community? Well, it seems like there's quite a bit of evidence, and I argue a lot of it's strong, for the production and accumulation, at least in pockets of the surface ocean and in other places, before the Great Oxidation Event. So it seems like oxygen is being produced perhaps as early as 3.0 billion years ago. We have a lot of good evidence from the Pongola supergroup. Some of you on this Zoom call are parts of those projects. But we don't have oxygen accumulating to any non-trace level in the atmosphere till the GOE, because it's just a mass balance game. Earth's surface is evolving, biology is evolving. The whole Earth system is evolving over, hundreds of millions to billions of years to become amenable to oxygenation. And you have to tip the scales in favor of oxygen accumulation. And so I'm not going to put my stock in any specific driver, but it seems like there's a lot of things happening to Earth's surface that would make it more amenable to oxygenation leading up to the GOE. And so it's not an oxygen production story per se, but more of the O2 sinks are diminishing in strength, and then you can get that oxygen accumulation. And as you start to approach this tipping point, it's not surprising to see these fluctuations where you're just tipping over the fulcrum. You're just passing the MIF sulfur threshold. And so if you can think of this as evidence of the whiff is kind of, we're reaching that tipping point for the GOE. And now we have sulfur MIF records extending into the early Paleoproterozoic that suggest that the sulfur MIF signal is reappearing also and disappearing in the Paleoproterozoic. And so it's an oscillatory rise. And I'm of the opinion that it seems to be just a mass balance game. Oxygen production and destruction is having a battle until oxygen production eventually wins and the GOE is over sometime around 2.2 or so. We're still trying to figure that out. All right, so shifting further in time forward, and for the last 9 minutes here or so, I'm going to focus on this idea of a Neoproterozoic oxidation event, which, like the GOE, it's a topic of contention among those in the community. And so it's been thought for quite a long time, since at least the late 1950s, and possibly before, probably before, that the rise of animals in the Neoproterozoic was a direct result of a widespread oxygen accumulation event. And it's a super intuitive idea, and it doesn't take much convincing that it's a good one. Animals have really high energetic demands, and so it would seem logical for their rise to correspond with the rise of oxygen. Perhaps there wasn't enough oxygen before the Neoproterozoic to facilitate animals, and it was this oxygen barrier that was removed and allowed them to rise. So it's an idea that it's been sold. It's been kind of the prevailing opinion of the community for many decades. And again, it's a logical idea. It makes sense for a lot of reasons. But there's this idea that it should be a thing. And then over the past few decades, there's a lot of geochemical data that's been pulled from the Neoproterozoic record that seems to suggest at least some of these geochemical trends are interpretable as evidence of widespread oxygenation. And so, you have animals appear in geochemical trends that seem like they're indicating oxygenation. It seems to support this hypothesis generally. And so this idea of this Neoproterozoic oxygenation event seems to be, it's not so much focused on the Neoproterozoic in general anymore. We're getting more and more data. We're getting better age constraints. This debate seems to be centered now, a lot of it on the Ediacaran period. And so it's in the Ediacaran period when you get the first fossilized, the first fossilized animals in the rock record, the Ediacara biota, the three assemblages of the Ediacara biota. So right after the gas gears glaciation, about 580 million years ago or so, you have the Avalon assemblage. And so you have the rise of animals around this time. At least that's what the fossil record, if it's read directly, tells us. And so, as was the case with these kind of broad stroke views of the Neoproterozoic, where animals, before we had all this additional data, it seemed like the Neoproterozoic was when animals appear. And we also see some geochemical trends in the Neoproterozoic that align with that. Seems like the story makes sense. And the same kind of result comes from a more detailed view, at least at first glance, that we now know these animals appeared in the Ediacaran, and we look at, for example, trace metal enrichments and shales in the Ediacaran, and we see really high abundances, which interpreted straightforwardly, would seem to suggest that you have widespread ocean oxygenation during the rise of animals in the Ediacaran. And so this is these redox-sensitive elements, uranium, vanadium, and molybdenum, are most soluble under oxidizing conditions. And so the idea is that in order to accumulate these elements to large abundance in seawater, you have to have a lot of oxygenated seawater. And by extension, you would also have a lot of these elements, these elemental concentrations in sediments would also be very high. And so this rise in the amount of uranium, vanadium, and molybdenum in shales seems to indicate a rise in the amount of these elements in seawater, and thus this widespread ocean oxygenation event. And so these are compilations from 2008, 2012, and 2013. And they all show that change in the Ediacaran during about the rise of the Ediacara. A few years later, there was higher resolution data sets, and it kind of adds to the intrigue. And so this is a Swapan Sahu's data set from 2016 in geobiology that shows in the Wuha section from South China and the Dowa Shantou Formation, you have these really strong trace metal enrichments that appear, term these OOEs, ocean oxygenation events, one right after the Maranoan glaciation, 635 million years ago, one perhaps 580 million years ago, and another one overlapping with member 4 about 560 million years ago. And so the direct interpretation here is that you have a generally anoxic ocean, and these blips of trace metal enrichments indicate transient ocean oxygenation events. And some of these oxygenation events, immediately predate the Avalon assemblage if the ages are right. So it's intriguing and could suggest that there's a paired evolution of oxygen in animals. And more specifically, not that there's just oxygen accumulation generally in the ocean, but the point that's made in some of these papers is that it's deep marine oxygenation. And so you've potentially got, this isn't my quotes, it's quotes in the papers, is that you have potentially near modern levels of ocean oxygenation during the Ediacaran rise of animals. However, and the reason that it's pulls in so much debate is that these trace metal enrichments are only found in the Dowa Shantou Formation from South China. If you go to other locations, for example, northwestern Canada, you don't find these trace metal enrichments at all, which is kind of curious. Furthermore, when you look at other geochemical trends that are interpreted by many as evidence of widespread oxidation, they don't seem to align in time. And so you've got these trace metal enrichment records from Swapan Sahu's 2016 paper, and you look at the Ediacaran Shurm excursion, the largest negative inorganic carbon isotope excursion in Earth's history, and that's interpreted by some as evidence of a widespread ocean oxygenation event. This event doesn't overlap in time with the trace metal enrichments for oxygenation. And so, in my view, it seems like, either one of these is correct or neither of them is correct. Well, I think that's a reasonable statement to make. They're certainly not self-consistent. So that's a little odd. And so getting back to the platypus, thallium seems like an ideal tool to test this hypothesis. If indeed Earth's oceans became very well oxygenated, perhaps near modern levels of ocean oxygenation, you ventilated the deep ocean, you're bearing a lot of ferromanganese crusts and nodules on the seafloor, you should be able to capture that with thallium isotopes. That's its unique sensitivity. And much like the Mount McRae shale, we should expect to see this really negative thallium isotope shift. If this is, if you're going from a Proterozoic as usual ocean oxygenation scheme to near modern levels of oxygenation, it should be a really strong signal. And so we've looked at a couple of sections now to this point, teaming up with some scientists and David Johnston and Eric Sperling to get some samples from northwestern Canada. And we find that our thallium isotope compositions in these rocks in northwestern Canada are all crustal. We don't have any really light thallium isotope compositions. Modern seawaters in blue there. We go to the Shurm Formation in Oman, which is where the Shurm excursion was first discovered. And we see across the Shurm excursion that we have no really light thallium isotope compositions in two separate sections there. And so we don't have evidence of this really strong manganese oxide accumulation event, even during the Shurm. And we put all of our data as best we can time individual samples, and we also have some samples from South China. We screen our samples for those that seem most likely to have captured a seawater thallium isotope value. During the rise of the Ediacara and across the Shurm excursion, we see no shifts towards light thallium isotope compositions. So at least according to the thallium isotope data that myself and my teams I work with are generating, there seems to be no evidence of widespread manganese oxide burial in the ocean during the Ediacaran. And so an interpretation of that is that there's not widespread marine oxygenation during the rise of animals, at least during the rise of the Ediacaran animals. And so I talk about all these ideas in a paper I recently published in EPSL that talk about the data that myself and my colleagues have generated that seems to support the idea of not a lot of oxygen during the Ediacaran rise of animals. But others in the community have pointed some other things out that seem worth noting as well, is that the substantial O2 increase that's often invoked doesn't seem to be required. The Ediacara biota don't look like they have really high energetic demands. And so why you don't, it doesn't seem like they need this widespread oxygenation event, certainly not ventilation of the deep ocean like we have today. My data seems to suggest also that the supporting evidence is complicated and inconsistent. Some of these don't align in time right. And yeah, the third point there is that there's temporal misalignments. One of the most important temporal misalignments seems to be the fact that now it seems that there is fossils from the Avalon assemblage that predate the Sherm excursion. And so if the Sherm excursion is this evidence for widespread oxygenation, then the fact that the Avalon assemblage predates the Sherm excursion kind of throws a wrench in that hypothesis that it was the oxygenation that drove the animals. You would expect to find the oxygenation evidence right before the rise of animals or during, but we don't. So maybe the null hypothesis is viable. Maybe there's no change in ocean oxygen. So just to conclude here, the first conclusion from my talk is that if you didn't know, hopefully now you do, or thallium isotopes are a strong and emerging paleoredox tool. It seems to have a really unique sensitivity and a really strong archive. Emerging evidence supports a dynamical great oxidation event, and so extending early, even into the late Archean, it seems like there's these transient whiffs of oxygen, and it even seems to persist into the early Paleoproterozoic. And then third conclusion, at least according to the data I'm generating, the Neoproterozoic oxygenation event merits continued investigation, at least during the Ediacaran. It doesn't seem like there's near modern levels of ocean oxygenation, at least according to the data that we're generating. So on the horizon, what am I most excited to work on moving forward? I thought it was worth showing is that myself and others are trying to move thallium isotopes into carbonates, and so more on that in the near future. What is the utility of carbonate thallium isotope ratios? We know it works well in shales, but what can we do with this potential archive? And so that's kind of a modern angle, but in the ancient angle is, so we don't find evidence of widespread marine oxygenation during the Ediacaran. Well, when does that happen? And so we're moving forward in geological time to find out when that ventilation event is. When, for the first time, do you have, over long time scales, oxygen accumulating in wide areas of the deep ocean? And so with that, I will leave a long list of collaborators who helped do all of this work. It goes without saying, but it's not just me. It's a lot of different colleagues have helped with the many projects that I presented on today, and I didn't pay for this myself. There's many funding sources that have helped pay for this, and I'll leave this up as I take any questions that you might have. Thank you.
Great, thanks, Chad. Good talk. We'll go ahead and switch to questions and discussion. You can raise your hand either by clicking the reactions button at the bottom, or you can type into the chat and I'll ask it for you. Greg Vitalik is already ready to ask a question. Please go ahead.
That was great, Chad. Really enjoyed that. And I love the idea that Dochanteau is different from the rest of the Ediacaran. I've always thought Dochanteau is a lagoon, a very restricted environment with even intertidal pyritic paleosols in it. But I don't want to go there. That argument could go on forever, probably. I want to return to Joe Kirschfink's objections to the whiff idea. It all comes out of one core, and his idea was that the whiff seemed to correspond to particular fractures that may have introduced modern hydrocarbons into it. I'd like to hear how you dismiss that. And also, it's only 30 meters of shale in a sequence that's pretty heterolithic with a lot of variation. Can you really rule out the sort of the Baltic Sea model for that shale as well? How do you deal with those objections?
Yeah, there's a bunch of questions in there. Let me see if I can get them all. First, a comment to Dochanteau, because I have an opinion in the fight, is yeah, I think there's evidence that suggests it's a really strongly restricted basin. A lot of people would strongly disagree with that, worth saying, but I'm up for that. There's a lot of data that supports that. I agree with that.
Excellent. Yeah.
For the ideas for the whiff, I'll first point out that a lot of the detailed information is in the Science Advances rebuttal,
Right.
but yeah, so those rocks.
I'd just like a take-home quickie. Yeah, what's the matter with it?
Yeah. So the matter with the hard thing the thing that's really hard to explain is the rhenium osmium isochron that's pulled out of the Mount McRae shell, and so we have it from those rocks with a really strong rhenium osmium isochron with a strong MSWD, and so it's really hard to explain how you can manipulate the molybdenum in that sequence. That's what the early whiff paper leaned heavily on the molybdenum enrichments. How do you manipulate the molybdenum but don't manipulate the rhenium? That seems hard to explain. And the evidence that the ideas that were put forward in the Sarah Slotsnik's paper, there were some holes in it. There was ideas of adding molybdenum with volcanics, but isotope fractionation mechanisms to drive the molybdenum isotopes required molybdenum removal, which is kind of counterintuitive. But again, yeah, I'll point you to the comment. One thing that wasn't, I think, mentioned heavily in the comment that's worth iterating here is that, and it kind of doesn't get brought up a lot, is that seemingly coeval shales from South Africa, so the Kleinout Formation, the geochemical data is much lower resolution, but we find the same signals in those core. So GKP01 and GKF01 from South Africa, we see really high molybdenum enrichments. In those shales, we have really positive molybdenum isotope compositions. Most of the geochemical evidence of a WIF in the Mount McRae shale is also found in the Kleinout. And so that's hard to explain if these two environments were deposited potentially 1,000 kilometers apart.
No, that's excellent. Because before then, it was just that one core, right, in the world for the WIFs.
Well, there's all the WIF paper in Science was published in 2007, and there was molybdenum concentration and isotope data from South Africa in the GKP01 and GKF01 cores. It was published in the same year. I don't know in what order, but Martin Willa has a paper in 2007 that showed high concentrations of molybdenum and heavy molybdenum isotopes in one of the cores, at least in the same year. Yeah. So the data aren't new, and there's at least some of the geochemical trends preserved in multiple cores. That data's been around for a long time.
No others besides those two, South Africa and Pilbara?
Yeah, we're really at the mercy of the ancient rock record, and there's not many good archives there. Those are the two best. All the others are pretty well cooked.
Actually, molybdenum enrichment is expressed in several other drill cores in Australia, like sort of in unpublished work by Hiroshi Amoto. He reported some enrichments, and when by Geological Survey of Western Australia, in a different drill core, they saw molybdenum enrichment.
Yeah, so decades before the WIF paper, I forget the year of that, Andre. You brought this to my attention some time ago, but yeah, decades before at least 1 decade before the WIF paper, there was high molybdenum concentrations reported for the Mount McRae shale, and you saw the enrichment across the upper shale member.
Well, thanks. That's very helpful. It's information I wasn't aware of. Appreciate your work.
Yeah, thanks for the question, Greg.
Okay, Chad, I guess I have a question. My understanding is that throughout the Ediacaran, there's quite a bit of variability in the uranium isotope record. So can you comment on why we're seeing that, but not much in the thallium isotope record?
Yeah, good question. And so I talk about this a little bit in that EPSL paper I published, as well as a geobiology paper where we published the data from the Shurm Formation. Yeah, you get a lot of uranium isotope variability, specifically across the Shurm excursion, where we see no thallium isotope variability. And so it's worth noting that those uranium isotope records come from carbonates. And so if you plot up the uranium isotopes in the carbonates versus the carbon isotope excursions that identify the Shurm, you get a pretty strong correlation, which to me is it gives room for at least continued interrogation that there's ideas that the carbon isotope signal is non-primary, perhaps a product of diagenesis, and the uranium isotopes trend strongly with that. I think is, it's not that I have a strong opinion, but in presenting my thallium isotope data that's invariant, I felt a need to talk about the uranium isotope data to try to reconcile it. And so there's still some kinks that need to be worked out, but that's one thing that comes to mind that's a little suspicious, and it's a shallower deposit. Carbonates are limestones have very reactive minerals. They're constantly reprecipitating and dissolving tens of thousands of times during early formation and burial. And you have changes in sea level that can really have strong, could be a strong lever on carbonate geochemistry, whereas the shale deposits we're looking at are further from shore, below wave base. They're not as susceptible to these changes. The environment is anoxic during formation. Diagenesis is probably anoxic, whereas the carbonate proxy for uranium isotopes, in order to capture seawater uranium isotope composition, it has to be locally oxic. And during diagenesis, that's going to change. Diagenesis will always move towards anoxic. And so there are redox changes subjected to that system that thallium doesn't see.
Okay. Thanks. Real quick before I move on to another question, and sorry if you said this early on and I missed it. What is the residence time of thallium in the oceans? I'm sure it's changed through time.
Yeah, sorry to not mention that. But yeah, the residence time of thallium in the ocean today is on the order of 20,000 years. So it is longer in the ocean mixing time of about 1,000 years, but its residence time isn't as long as some of the other molybdenum and uranium proxies, which are on the orders of hundreds of thousands of years. And so what was the residence time of thallium in the ancient ocean? Who knows? It's difficult to get at that question, just like it is with molybdenum and uranium. But it's worth noting that thallium delivery to the ocean isn't redox sensitive, which is kind of nice. Whereas, like in a low O2 RT in a Proterozoic world, you don't expect much molybdenum or uranium to be weathered from the continents and delivered to the ocean. Thallium doesn't seem to have those same barriers. And so like low O2 in the Archean or Proterozoic wouldn't slow thallium delivery.
Interesting. Cool. Thanks. We have one in the chat from Kay Sunder. How long did the oscillatory phase between oxygen sinks and sources around the start of the GOE? Were those oscillations dampening over time, and does this correlate to the magnitude of any geochemical processes?
Yeah, so in terms of how long did it take, I think we're still trying to figure that out. There's evidence of early, potentially an earlier whiff than 2.5 billion years ago. There's evidence of a whiff potentially at 2.65. So maybe it starts there. There's still, when does it start and when does it end? How do we define that? It gets difficult. I think most would lean on the sulfur MIF proxy for at least the end of the GOE and the end of the oscillatory nature. And so we're still, I think, actively trying to figure out when sulfur MIF disappears forever. And so there's evidence from Simon Polton and others in 2021 that extends it to about 2.2 GA. And so it's something on the order of, approaching a half a billion years, it seems, which is quite a long time. In terms of like changes in magnitude, I think was a part of that question. You can get an opinionated answer from me because I've worked a lot in that time frame, but I think the geochemical signatures for oxygenation do get stronger with time. This 2.65 billion year old early whiff is really, really muted and kind of hard to pick up geochemically. The whiff seems to be much more substantial. And now the evidence that we're pulling from the Paleoproterozoic seems to be even more substantial oxygenation yet. We're starting to kill the sulfur MIF signal. And so it seems like it is increasing with time, which suggests that you're getting progressively stronger whiffs of oxygen, which would kind of make sense in this mass balance scenario. In terms of drivers, I said I wasn't going to mention it, but because you asked, I guess I'll give some opinions. I think the idea that you hydrogen loss from the upper atmosphere is a net oxidant to Earth's surface over time. I think that's something that is an idea that's simple and attractive. And now there's xenon isotope records that seem to paint that picture pretty eloquently. And so I think hydrogen escape from the upper atmosphere is something that's really acting as a strong through time net oxidation of the surface, among others. There's a lot of other different ideas of what's changing around there.
Great, thanks. Shuhai, please unmute yourself and go ahead. Shuhai, are you there? Well, maybe he stepped away. So I'll go. I'll hit Lyle's question and then come back to Shuhai. So Lyle Nelson, he can't unmute himself. I should. Okay, Shuhai, I sent you a request to unmute. Did you get that? If it's not working, you can type it up and I can ask it for you. Okay, I'll ask Lyle's in the meantime. So Lyle Nelson asks, most of the Ediacaran macrofauna post-Avalon assemblage appear to be living in shallow waters. If there was increased oxygenation in shallow waters, would you see this in thallium isotopes, or are the manganese nodules or crusts volumetrically forming in deep water? In other words, would there be a shallow water oxygenation lever in the late Ediacaran, early Cambrian that is not seen in thallium isotopes?
Potentially, yes. The answer could just be those two words. Yeah, so you hit it right on the head, Lyle. It's a possibility that thallium isotopes won't be able to capture that transition if that's what it is, just a shallow marine event.
All right. Yeah, he says, thanks, great talk. Okay, we're waiting on, or Shuhai is typing his question. Andre, did you try to speak up earlier? Did you have a question?
Yeah, but I think Shuhei
Oh, there it is.
typed
Okay.
his.
Yeah, could you clarify this? You said that thallium isotopes in sediments of modern restricted basins show open ocean signals. That's from Shuhai.
No, it's the opposite. So in restricted basins today, they have local seawater thallium isotope compositions. The Black Sea has its own seawater isotope composition. The Baltic Sea has its own as well. And it's dictated by what's the primary thallium delivery mechanism to those basins. And so for the Baltic Sea, it's modern rivers. For the Black Sea, it's modern rivers. For the Baltic Sea, it's modern rivers as well. There is a slight anthropogenic fingerprint in the Baltic Sea. More on that, hopefully in a few months. But yeah, it's we studied also a small pond on Cape Cod, Sitter's Pond, that is subjected to some of these effects as well. It's just, what's the primary thallium input? And so these restricted basins have their own seawater signatures. And so yeah, if you look in Earth's past, what's kind of nice about that, the way it works out, is that they kind of all normalize to river values, which haven't changed much with time, we think. And so a restricted basin would have a thallium isotope composition of -2 epsilon units. And there's another follow-up question that I'm sure that could come up from that is all the Ediacaran data from restricted basins? Yeah, I guess it's something we can't confidently say, definitively. I'm answering a question you didn't even ask, but yeah,
he followed up, so maybe that can help correct. What drove the oscillations in thallium isotopes of the Doshanto?
Oh man, that is a data set that keeps me up at night. So yeah, so the Doshanto formation, we have the largest negative thallium isotope compositions we've ever generated in any sets of ancient rocks. And it's not a shotgun blast. We have really beautiful coherent trends. The answer to your question, Shuhai, is we still don't know. That is such an odd signal. We've been trying to study different modern settings to try and find the modern equivalent. But we just haven't been able to find it. That's a super weird data set. One thing that I think is worth pointing out with that data set, though, and is that the idea that these trace metal enrichments, all that data is from the Wuha section, which is the same data that the section that Swapan Sahu had targeted. We have these pulse trace metal enrichments. They're really easy to find. They're big. They're easy to see. And so, when we came to this set of rocks, we had an easy hypothesis to work off of is during these redox sensitive element pulses, we should find really light thallium isotopes. If this is such an easy interpretation of oxygenation, that should be an easy data set to pull out of these rocks. But all these really negative thallium isotope shifts actually occur in between redox sensitive element enrichments. And it's just so hard to explain. We have a couple ideas we put in our manuscript in chemical geology in 2020, but they're really hard to explain. My preferred interpretation in the 2020 paper was that the Doshanto is a restricted basin, and so it's much easier to sway the mass balance of a small body of water than a large body of water. And so if you have a restricted basin, there's a couple of processes that you can envision that could really change thallium isotope mass balance locally. It's really hard to drive that signal over a large area of the ocean.
So another follow-up was, do the uranium isotopes show oscillations coupled with thallium isotopes?
I imagine this is still an Ediacaran-centric question.
Yes, same. From Shuhai, same on.
Yeah, so if it's a follow-up for the Wuha section, I've never seen any uranium isotopes from the WUHA, it'd be that would be a fun project to do, to see if the uranium isotopes trend at all with the thallium in the WUHA. The thallium and the uranium certainly don't trend together across the Shuram. You see big shifts in uranium across the Shuram, and thallium doesn't move at all. It's worth noting that we also measured molybdenum isotopes in the WUHA section, and we'd get no strong coherent relationship there as well. So if you're in the market for generating weird geochemical trends, then go to the Doshanto formation.
Mm-hmm. He says thanks. Andre, did you want to go now?
Yeah, sure. I have kind of two questions, sort of unrelated. So first one, let's say if you go to Archean and with no atmospheric oxygen, what would be your predictions? So, sort of, you said that thallium is not dependent on redox, but thallium is probably hosted in sulfides. So in that sense, probably would be less flux of thallium coming from continents. And then can you talk about hydrothermal flux? It seems like low temperature alteration, I presume, release some thallium with probably positive thallium isotope values. So would you predict that seawater before oxygen in surface environments would have positive thallium isotope values, and thallium concentrations would be low in sediments?
Yeah, so see if I can get all these. The first question was on like thallium hosted in sulfides on the continents. And so there's plenty of thallium in continental sulfides today, but thallium delivery from that mechanism is not the predominant thallium input source. And so I wouldn't imagine it would be a substantial source in the Archean. It wouldn't change things much. In terms of low temperature hydrothermal alteration, it's the basalts surrounding these systems that get enriched in the lighter mass thallium isotope for reasons we can't quite understand. The thallium that comes out of those events is not positive. It's actually it's crustal. It's the same as bulk silicate earth / percontinental crust. And so changes in hydrothermal thallium input, at least according to the few data points we have, doesn't seem to suggest that it would change thallium isotope mass balance. But it would bring a lot of thallium in. There's, the most efficient thallium removal mechanism that we're finding in modern settings and experiments is sulfide. And so thallium removal in the presence of sulfide is very rapid, much more rapid than, for instance, molybdenum. Thallium drawdown below the oxycline in the Black Sea is much more rapid than molybdenum. The same in the Baltic Sea and the same in Kuriako Trench. Thallium really is efficiently removed in the presence of sulfides. And so if you're going to really shunt the size of the seawater thallium reservoir at any time in those past, I think it's at times when you have really widespread sulfide accumulation. And other times, there's little reason to suspect you would draw down a lot of thallium. The only reason that manganese oxides are able to draw so much thallium today is because they just cover such a large area of the seafloor. These are actually really inefficient removal mechanisms. These things form so slowly. The thallium accumulation rates are so small. You asked a lot of questions in there, Andre. Did I gloss over all of them, at least?
So basically, sulfidic ocean or extensive Euxinian ocean would be drive thallium down, right?
Yeah. So one point that's worth making is the thallium concentrations that we pull from the Mount McRae shale in the Archean are really high, like a couple of ppm. That's about as high, if not higher, than we're finding in modern sediments. And so really high accumulation of thallium in those shales seems to suggest there's a lot of thallium around.
And the second question, kind of, I don't know if you have answer, but kind of to contrast Neoproterozoic and Paleoproterozoic. So like as Lyle said, you can reconcile your thallium data and oxygenation if you have only shallow water oxygenation and deep ocean wasn't oxygenated. But if you take it now to Mount McRae, how do you explain that in Ediacaran, when was plenty of oxygen, at least in atmosphere, you couldn't oxidize deep ocean, and in Mount McRae, when it was short events and probably less intense, somehow it was able to have a larger impact?
Yeah, I'll be blunt. I've asked, this question's been asked quite a few times. It's an obvious one to ask. Yeah. And so maybe it has to do with sulfide. You have very little, perhaps you have some sulfide accumulation in the Neoproterozoic that makes thallium removal much more efficient. I think it also has to do potentially with manganese chemistry. And so today, manganese oxide formation is actually kind of limited by manganese availability. There's plenty of oxygen to oxidize manganese, but there's not a lot of manganese in seawater because all of it's been insolubilized. Whereas you can envision perhaps in a stratified Archean or Proterozoic ocean where you have a large dissolved manganese reservoir, in areas where this high manganese contents are being upwelled onto the continents into oxygenated surface waters, you would get a lot of manganese oxide burial. And so it may be that the efficiency of manganese oxide formation near redox clines in the ancient ocean was very efficient. And so you could get a lot of thallium removal and other metals in those settings and drive like a disproportionate effect relative to today, just because manganese oxide formation and burial is so much more efficient than you have a lot of manganese coming up into these oxygenated settings. Maybe the Ediacaran was a little different. Maybe sulfide plays a role in helping dampening the rise of thallium in the ocean. One thing I also think about is the preservation of this may be a bad idea. I don't know. It's one I'll say anyway. But the Ediacaran biota, their presence in the rock record seems to be facilitated by widespread microbial mats. And so the seafloor during the Ediacaran was covered in microbialites. And so what effect does that have on thallium isotope mass balance? So what's the thallium isotope fractionation effect of a sediment covered by microbialite? I guess the same thing kind of happens in the Archean. But does that make it hard to bury manganese oxides anywhere? The deep ocean is limited because there's very little oxygen. In the shallow ocean, the microbialites, which bring the redox cline perhaps closer to the sediment water interface. Is that shunting manganese oxide burial everywhere?
So maybe it would be interesting to study this shales around Phanerozoic manganese deposits where you have restricted basin and manganese upwelled to shallow redox cline. What does it do?
Yeah. And so this is the type of environment maybe, it'd be exciting to look for to try to explain the data we find from the Wuha section in the Doa-Shantou. That's, you have to have a restricted basin with a lot of manganese oxides. Those are two ingredients that would be really helpful to do that.
Okay. I think Greg has questions.
Go ahead, Greg.
Shuhai's perceptive question has got me going on the Doa-Shantou, and I can't wait to dive into your paper that you mentioned, which I have actually missed. My inspection of the Doa-Shantou showed two kinds of paleosols. There's paleokarsts, which are red and include cave deposits. I think Shuhai agrees with those. But I also noticed that there were quite a number of strongly pyritic paleosols that have a very strong redox gradient from top to bottom, which would resemble the sorts of soils you would get these days in a tidal flat, in a mangrove or a salt marsh environment. So my question is, do we know anything about thallium isotopes in paleokarsts and in mangrove soils?
No.
I thought that'd be the answer, but it's bound to be weird, right? And you're getting weird, so maybe there's hope or something interesting there. Who knows?
Sorry for not having a more eloquent answer. Yeah.
Yeah, very good. Anyway, very thought-provoking. Thanks a lot.
Thanks, Greg.
Great job.
I think we're still kind of closer to that Doa-Shantou question. Paul asked any lower Datong Po thallium data? Question mark.
Same answer as the last question. No, we don't have any Datong Po data. Yeah, it'd be interesting to generate and complement it with coeval sections. That's kind of what we've done with the Doa-Shantou and the Ediacaran. Is we started with the Doa-Shantou and we've found these really weird trends. And since then, we've moved to many different paleo basins. We've done the stuff in northwestern Canada. We've looked at other sections in South China. We've looked at the stuff from Oman. What's the weird stuff and what's the real stuff? And we get much more what seem to be coherent and consistent pictures from the other settings. It seems like the Doa-Shantou is the odd duck. And there's other geochemical signatures for which that's the case. The trace metal enrichments, the really light molybdenum isotope compositions that seem to just destroy molybdenum mass balance rules. Yeah.
All right. We have another one from Lyle Nelson. Have you measured whether banded iron formations have a large thallium fractionation? Can volumetrically significant deposition of banded iron formation drive thallium shifts in the early Paleoproterozoic?
The most direct answer is no, we don't know because we haven't measured them. But there's some hypotheses that can be thrown out there. It depends on what these iron formations, what their precursor phases were. And so if we have no idea what thallium does with green rust, we have a little bit of idea of what thallium does with oxyhydroxides. And so there's a slightly positive thallium isotope fractionation effect with oxyhydroxides. And so maybe that could drive a small effect, especially if they cover a large area of the seafloor. But that's definitely a room for more research. It's more thallium experiments with different iron oxide minerals, I think, is due. There's little reason to suspect that thallium gets oxidized on the surface of an iron oxide from thallium plus to thallium 3+, which is what you need to do to drive the positive isotope fractionation effect. So even the one oxide that's been measured to this point and shows a small fractionation, some more work needs to be done to try to figure out what's actually happening there in more detail. Some more studies.
Okay. Kaysen Dur asks, is thallium sensitive enough to accommodate for manganese from hydrothermal vents and it says, and allied bacteria? I'm guessing microbial processes related to hydrothermal vents.
So in terms of like hydrothermal manganese oxides, there is a higher, more positive thallium isotope compositions in the hydrothermal manganese oxide deposits. It could be because they have a small amount of hexagonal bernesite that's getting into the signal, or it could be that they're comprised of those more hydrothermal minerals like todorokite and triclinic bernesite, and it's just a muted fractionation. In terms of the biological aspect, in terms of biology around vents, this is we're much farther behind in our progress than that. We haven't tested that question specifically. That's a pretty detailed one. We're not close to that one yet.
Okay, I have to guess another one. Do you have a sense of how thallium, I'm guessing it shouldn't fractionate, but how it deals with autogenic clay formation?
Yeah, so this is work that's ongoing in another group. So the answers hopefully will come in some amount of time. But yeah, we don't quite know at this point. Thallium does have an affinity for clays, being the same charge and size as potassium plus. Thallium is happily incorporated in with clays. But whether there's an isotope fractionation, the mechanism for this strong nuclear volume shift effect, this oxidation, there's little reason to think that you would get the oxidation. But it's something that still should be tested. Yeah.
Yeah, I mean, if there's something to really dig into there, I mean, if we can start to isolate some of these, if these, iron silicates in the iron formation record are truly primary, then being able to isolate that and study that might, give an opportunity to look into a different part of the record.
Yeah, just one hesitance I have with thallium and banded iron formations is modern analogs are non-existent, and debates are plenty on what the precursor phases are, and so it's a really hard it's really hard to form a hypothesis of what you might expect. And I imagine that the results will be a little funky. Yeah, and we don't know why, I think, just yet.
Yeah, I wonder though, I mean, to some degree, like, yes, there's no modern, and maybe this is kind of getting speculative in a broad sense, but that isn't specifically related to thallium. But I mean, there's obviously no modern example, but when it comes to autogenic clay formation, that's happening and has always been happening. And like, we might not have greenolite, or we might have greenolite in some places, but we do certainly have like autogenic, iron-rich aluminosilicates forming. We have a record of berthrine and chamosite and such, that I wonder if just studying modern clay formation could, result in realistic, a realistic insight into that record. I mean, do you think definitely not because they're not happening in the same environment?
I think the idea is the the understanding we have for thallium and thallium isotope fractionation systematics today, I'd certainly come at it with the hypothesis that it wouldn't drive substantial effects. But, you know, as is often the case in science, you might be surprised by the result, and so you need to do it anyway. And those are actively being done by another scientist.
Cool.
Francois Osa seems to be working on it, so I look forward to the finds.
Cool, thanks. Okay, doesn't look like anybody else has questions to discuss. So thanks a bunch, Chad. That was a great discussion, great talk, etc. So really good contribution to the series. Thanks.
Awesome. Well, thanks for the invite, and it was a pleasure.
All right, everybody, take care. See you next week.